Welcome to video lecture F1. This one is on eigenvalues and eigenvectors. I'll be your bard, Tom Roby. The reason that we're now in the F's is because E's were already taken, so I couldn't use eigenvalues. And this is more generally about matrix factorization, so that's what started with F. Here are the outline and objectives for this one. We're going to memorize the fundamental definition of an eigenvector and its corresponding eigenvalue for any square matrix, A and R to the n cross n, and we'll visualize it geometrically. Then we'll analyze how row reduction can be used to find the eigenvectors corresponding to a given eigenvalue, and we'll explore basic properties that follow from definitions. So the first thing to point out here is that we have eigenvectors and eigenvalues, and you want to keep them straight even though they look the same. So here's the motivation. We often find ourselves in a situation where a matrix indicates how something updates over time. For example, you might have some economic situation where every month, if you apply this matrix to the vector of the current state, that'll tell you what happens next month. And you can project forward to a few months if you think that conditions are likely to, if the update is likely to be the same from month to month, then taking powers of the matrix. Actually, if you want to know what's happening a year from now, then you would take a to the 12th power and apply it to the current state vector to get what you predict would happen in a year. So these kinds of things happen all the time. They're discrete dynamical systems involved with, looking at population growth and various things. There's a whole range of situations. And eigenvalues and eigenvectors are key to understanding those kinds of situations. And in particular, what we're looking for are a better basis. If you have a matrix that's n squared numbers, that's hard to deal with. If we can find a better matrix with respect to which things are, the matrix is actually triangular or even diagonal, if we can hope for that, then we have a much easier time of analyzing what's happening as we repeatedly apply a process. So these things, eigenvectors and eigenvalues, only apply to square matrices. So it's only something where you can apply them over and over again to vectors of the same length. So we have vectors in R to the n, and we have a matrix in R n by n. And here's the thing, we have to have a non-zero vector. So the vector, an eigenvector is always non-zero. But if we can find a non-zero vector satisfying this crucial equation, ax equals lambda x, then we'll call x an eigenvector of A, and lambda will be the corresponding eigenvalue. Now, you should think immediately about what this means. What does this mean? In general, if I've got some input vector, maybe pointing this way, the output vector could be pointing this way or that way or some other direction as well as being stretched. We've looked at two-dimensional transformations that do a variety of things. In this situation, if we have an eigenvector-eigenvalue pair, the eigenvector is special because when you look at how A operates on it, it just stretches it or shrinks it in along the same line. It could also do the negative. It could flip its sign, but it can't change the way it points except changing it from positive direction to the negative direction. That's all it can do. So an eigenvector is a very special kind of vector that when you apply the matrix to it, you get a multiple of that vector. The multiple you get is called the eigenvalue. So if you have an eigenvector and the eigenvalue is 2, then that means that when you're looking at things along that direction, they all get stretched by a factor of exactly 2. Eigenvectors and eigenvalues come in pairs, and there's a lot we'll be able to say about them, and they're incredibly useful. They're fundamental in the whole rest of the course. But this ax equals lambda x, that's the fundamental equation, and we'll be able to do a lot just with that alone. And so it's worth thinking about that before we get into other kinds of techniques. Let's see. So let's look at an example right away, a concrete numerical example. Here's a 3 by 3 matrix, and I'm giving you the pair. So the eigenvector is 3, 1, negative 1. How do I know it's an eigenvector? Well, if I apply this matrix to it, I get, and you can check this, 9, 3, negative 3. And that's just 3 times 3, 1, negative 1. So that means that 3, 1, negative 1 is an eigenvector, and it corresponds to the eigenvalue 3. Okay? So it's not hard to check. If I give you a vector, it's not hard to check whether it's an eigenvector or not. You don't even know what the eigenvalue is offhand because it'll just occur. But here, for example, if I apply a to 1, 1, 1, I get something negative 173. That's clearly not a multiple of 111, so 111 is not an eigenvector for A. Now, we'll get into how to find eigenvalues in future lectures, but a question that we can answer right now is, if I know for some reason that 3 is an eigenvalue, how can I find a corresponding vector to that lambda? And here's the answer, and it all follows beautifully from all the work we've already done. If you want to know whether ax equals lambda x, that's equivalent to saying that a minus lambda I times x equals 0, right? Because lambda x is the same thing as lambda times the identity times x, right? And I want to have the identity in there so I can conceptualize properly a minus lambda applied to x. I really mean a minus lambda times the identity applied to x. Because now I have, and this a minus lambda times the identity, well, that's just some other matrix, right? It's a matrix where I've subtracted some things off. So if I apply that to x, I should get 0, right? Because I move this over to the other side. So that's just saying that x, the vector x, has to be in the null space of a minus lambda I. So this crucial set of equivalences shows you that eigenvectors are nothing more, if you know the eigenvalue, then they're just any vector in the null space of a minus lambda I is a perfectly good, will be an eigenvector corresponding to that eigenvalue. All right, so how does this work? So for example, here, if I look at, I know that 3 is an eigenvalue. Suppose that's all I know, that I didn't actually know what the eigenvector corresponding was. Then I have a minus 3i, right? So I subtract 3 from all the diagonal entries. That's what a minus 3i does. So I get a negative 1 instead of a 2, and this 1 becomes a negative 2, and this 4 becomes a 1. The rest of the matrix stays the same. I do row reduction. I look and I see, okay, so now it's a square matrix. So either I'll get a row of zeros, or I'll have 3 pivots, and there won't be any eigenvectors. So if I'd done this with, something like 7, which is not an eigenvalue, a minus 7i, I could do the row reduction. I'll get a matrix that's full rank. There won't be any, there won't be a row of zeros. Okay, so there can only be free variables if there's a row of zeros for a square matrix. So I've got a row of zeros. That means I've got a free variable, and you can use the standard thing to check. Okay, this is saying that x1 should be negative 3x3, right? And look at if x3 is 1, then I get negative 3. And this is saying that x2 and x1 should be negatives of each other, and that's true too. So that's how I got that vector. Okay, so given an if I know what the eigenvalue is, then I can find the corresponding eigenvector easily using the standard Gaussian elimination. We're really lucky that Gauss is no longer alive, because we would have to pay royalties to him for all the times we use Gaussian elimination. And now to start wrapping our brain around this, it seems like a simple thing to state, but eigenvalues are really a rich and complex idea, and so it'll take a while to fully come to grips with everything that we want to be able to do with them and say about them. But here's a simple question. What can you say about eigenvectors for lambda equals 0? So remember, 0 can't be an eigenvector. The 0 vector can't be an eigenvector. But the 0 scalar can be an eigenvalue. That's perfectly fine. So what would that mean? Well, if you go back to basics, you'd be saying that a times x is equal to 0 times x. In other words, ax equals 0. Okay, well, we know what ax equals 0 means. That means x has to be in the null space. Okay, so if we've got, an eigenvector for x, an eigenvector for lambda equals 0 is just a vector in the null space. Okay, so sometimes people talk about eigenspaces. You notice I said here x is in the span of negative 3, negative 1, 1. And the eigenvector I originally gave you was 3, 1, negative 1, which is not exactly the same. It's a multiple of this, right? So if I have a vector as an eigenvector, then any multiple of it will be an eigenvector. And if I've got a bunch of different eigenvectors corresponding to the same eigenvalue, then any linear combination of them will actually also be an eigenvalue, because this equation is linear. Okay, so the answer to this question is that the eigenvectors are the elements of the null space. Okay, so now let's look at some basic properties, things that we don't need a lot of machinery for, and work them out one by one. So question 1, if x is an eigenvector for a corresponding to lambda, what about a squared? Okay, so, well, what do we know? The fundamental equation is that ax is equal to lambda x, right? Now, what about a squared? Well, I can apply a to this whole equation, right? So I end up with a times ax is equal to a times lambda x. Now, multiplying by a matrix is linear, right? So this becomes a squared x on this side. And now here, I can pull this lambda out, and this is just equal to lambda times ax. But now, lambda, I know that ax is equal to lambda x, right? So this is lambda times ax, which is equal to lambda times lambda x, which is equal to lambda squared x. Okay? So this simple chain of equalities shows me that a squared, if lambda is an eigenvalue for a, then lambda squared is an eigenvalue for a squared. And in fact, the eigenvector is the same vector, right? So the vector that worked here that told me that ax equals lambda x is the same vector that told me that a squared x equals lambda squared x. Okay? So if x is an eigenvector for a corresponding to lambda, then x is also an eigenvector for a squared corresponding to lambda squared. Okay, next. If x is an eigenvector for a corresponding to lambda, what about a inverse? Well, you can do a similar kind of analysis. So I'll leave it as an exercise for you to see that. So exercise, show that lambda inverse is eigenvalue for a inverse. Okay? So that sort of shows you in general, you know, and so the general fact is that lambda to the n is an eigenvalue for a to the n if lambda is an eigenvalue for a. And that applies for n, any integer, positive or negative. Okay, what are the eigenvectors and eigenvalues of a diagonal matrix? Right? We'd like diagonal matrices because they're easy to manage. So let's see what happens. Well, suppose I've got I don't know, let's just, it's easiest to do an example and see that the reasoning is general. So if I've got something like, you know, 2, -1, 3, and then I've got zeros everywhere else, right? Let's see, make that 3 over there. Then I claim in this case it's actually really easy to understand what the eigenvalues are. There we go. Right, so it's really easy to understand. We'll understand the eigenvalues and the eigenvectors. So here's the point, right? What vector could if I apply d to it, do I obviously get a scalar multiple of it? Well, in the diagonal case, if I take the standard basis vector 1, 0, 0, then my output is going to be just 2, 0, 0, right? And that's just 2 times 1, 0, 0. And similarly, if I did, say, applied this matrix to 0, 0, 1, then what would I get? Well, I'd get 0, 0, 3. Okay? So the point is that, and similarly, if I did 0, 1, 0, then I would get the -1. So when I have a diagonal matrix, the standard basis, so maybe I can write that here. Standard basis vectors are eigenvectors, sorry, and they correspond to the diagonal entries. Okay. So this is one of the easiest cases to understand, but it's really good because one of the things that we'll try to do later is take more complicated matrices and diagonalize them. Figure out how to change the basis so that we get them in diagonal form. And then once they're in diagonal form, we know that whatever basis that we wrote, that we used to create this diagonal form, that's the basis with respect to which, that's the basis of eigenvectors. Okay. Now, how can we visualize the action of a diagonal matrix geometrically? Well, here we've got a 3 by 3 matrix. If I multiply, if I've got something if I've got the E1, then it just stretches it by 2. And so if I only had a 2 by 2 matrix, let's say 2 and 3, then it would be taking the square and stretching it into a rectangle, stretching it by 2 this way and 3 that way. In this case, we have to think about it doing 3 dimensions, and so it's stretching in the x direction by 2. It's stretching in the y direction. It's pointing back by -1, right? So it's reflecting, and then the 3 going up, it's going to take the standard basis vector and make it 3 times as big. So that's the way you think about stretching and shrinking for the diagonal matrix, but it's exactly what happens with any eigenvector, just with respect to pointing in different directions. Okay, so now here's an interesting question. Must every matrix have eigenvalues? And so you might want to stop and pause for a minute and think. Can you think of a matrix that wouldn't be able to fix, to have any vector that pointed in the same direction that it did originally? Okay, so now I'll tell you the answer is, well, you can have a rotation matrix. So if I let R be the matrix that, so how do I write the matrix that rotates me by 90 degrees? So I'll draw, so it takes E1, the output of E1, if I rotate it by 90 degrees, it goes here. So with respect to this basis, E1 maps to E2, so that's 0, 1. And E2 maps to this to -1, 0, right? So this is -1, 0. So that's the rotation matrix R. And now if I think about what that's doing geometrically, well, it takes every vector and it rotates it by 90 degrees. So no vector ends up just remaining pointing the same direction that it did before. And the only point that's fixed is the origin. So there's no, but 0 can't be an eigenvector, so there are no eigenvectors. And therefore there are no eigenvalues because they come as pairs. Now in an upcoming lecture, we'll see another reason to see why, using the characteristic polynomial, we can see that there are no real roots to this. And this matrix could have complex eigenvalues, but we're not thinking about those right now, although they are useful in some applications. Okay. If x and y are eigenvectors for A, does their sum also have to be an eigenvector? Now this is a bit of a trick question, so let me take you through it carefully. So let's see. Joint. Suppose that x and y are eigenvectors corresponding to the same lambda. So if you assume it's the same lambda, then what you'll end up having is something as follows. Maybe I can write down here now. I think I've got space. Right, so if I know that ax equals lambda x and ay equals lambda y, same lambda, well, that implies that a times x plus y is equal to a times x plus a times y by linearity, but that's equal to lambda times x plus lambda times y, and that's just lambda times x plus y. Okay, so a times x plus y is equal to lambda times x plus y. So x plus y is an eigenvector corresponding to the same eigenvalue lambda. But if, for example, these were both eigenvectors but for different eigenvalues, suppose ay was actually equal to mu times y instead of lambda. Well, then I'd have, this would still be true, but then I'd have lambda x plus mu y, and this last step wouldn't work. Okay? So it's important, you can have eigenvectors corresponding to different eigenvalues for the same matrix, and so the sum of two eigenvectors may not be an eigenvector unless they both correspond to the same eigenvalue. And you can easily show similarly that a scalar multiple of an eigenvector is also an eigenvector for the same thing in the linear combinations. If x and y are both correspond to the same one, then any linear combination of them will. So you really have these things called eigenspaces, which are vector spaces of eigenvalues. Okay, and the last question is, if lambda and mu are both eigenvalues for A, must lambda plus mu be? So this is the kind of true-false question that you might get asked in some situation, you know, a chimera quiz or on a final exam or something. And so it's good to be able to come up with simple counterexamples, right? That's a fundamental skill that you need to do mathematics, is to think about, is this true or false, and what are the examples that show that it doesn't work all the time. So here, I need an example. I need a matrix A that has two different eigenvalues, but maybe its sum doesn't have it. And it's actually easy enough to write down just something like 1, 0, 0, 2. It's always best if you can write a simple example, right? Because here it's obvious that the eigenvalues, that 1 and 2 are eigenvalues corresponding to the eigenvectors E1 and E2. And when we get a little bit more theory, we'll see that matrix, an n by n matrix, can't have more than n eigenvalues. So this one has two eigenvalues, 1 and 2. That's all it can have. And 3. So 3 is not an eigenvalue for this. You could also just see directly that 3 is not an eigenvalue of this matrix, because if you look at, so I don't know what I'll call this matrix, maybe D for now. If I look at, you know, say D minus 3 times the identity, what's that? Well, then I'm going to get negative 2, 0, 0, negative 1, right? Now this has a non-zero entry in every diagonal entry, so this is row equivalent to the identity matrix. So it's an invertible matrix. It doesn't have a null space, and 3 is not an eigenvalue of it. Okay, so those are the real basics, but they're fundamental basics for eigenvalues and eigenvectors. And you might want to come back and look at these slides again, or even revisit this video after you've done a little bit more work with it to see what can be done just from basic principles, because people often get lost in using higher level machinery after they've seen a little bit of it. Anyway, that's it for today. Thank you for your kind attention.